Okay, ATP synthase. So if you look back a step, we'll go back one, wrong way. So back to this diagram. If you notice on this diagram, I have the intermembrane space up here and the matrix down here. And we can see the protons are getting pumped into the intermembrane space from the matrix. 4 at complex 1, 4 at complex 3, and 2 at complex 4 again. And then those are allowed to, with the gradient, fall back down, if you will, but fall through the gradient, if you will, through ATP synthase, and it powers ATP synthase. If you notice, though, I drew the intermembrane space on top, I drew the matrix on bottom. And then I decided to mess with your head and draw ATP synthase here, and now I've got the matrix on top, and I've got the intermembrane space on the bottom. Now, is there a proper way to do this? Is it proper to put the matrix on top, or is it proper to put the matrix on bottom? It doesn't matter. So, and here's the deal. I put it both ways on purpose. So, because some books show it one way, some books show it the other way. Some professors show it on their slides one way, and then they show it another way. You could see it showing up either way on the test, and the problem is we're visual people, most of us. And I see a picture, and I'm like, yep, there's the matrix, and there's the intermembrane space, or vice versa, on whatever picture I studied off of, and then I don't realize that they just turn the whole picture over on the test, the diagram they give you. So, just keep in mind, they can draw it any way they want to. You need to memorize it not from a visual perspective only, but also which side really is which. So the matrix side is where the F1 ATPase activity is. So, and then F naught is in the membrane. So F naught has protein channels. These proton channels. Protons are going to flow through. That's going to cause the F1 to spin, to rotate, and as it rotates, we get ATP synthesis. We're going to focus a little more on that particular process. So I have hated almost every diagram I have ever seen like this. Almost every one. They're so confusing. So hopefully we can eliminate some confusion here, but you do got to know how this works. So this is kind of a top-down look at the F1 ATP synthase moiety. Question?
Does it matter if you show it moving clockwise or counterclockwise? Because in our notes you said counterclockwise turn, but as long as you know the order, it's fine.
Yeah, as long as you know the order, you're okay. It doesn't really matter. So again, there's a piece of arbitrariness there as well as whether clockwise or counterclockwise. So in this case, I'm going to go clockwise. But again, as long as you know the order, you're okay. So if you look, there's 3 different beta subunits, and it's the beta subunits that have the catalytic activity. There are also 3 alphas that are not part of this diagram. If you notice, the beta subunits here represented by O, L, and T, or black, blue, and red, if you will. So they're the catalytic ones. I've kind of ignored everything else, but they're hinging on the gamma subunit in the center there. So if you look, the T site here is the one that actually converts ADP to ATP. I'm starting out here assuming that it's already converted an ADP to ATP. That's a freshly made ATP sitting right there. Cool. So first thing that happens is your L site, which loosely binds ADP. So, well, it needs to loosely bind some ADP. And so ADP and inorganic phosphate are going to bind to your L site. So notice your ATP is still bound to the T site. It's still freshly made, just sitting there waiting. So now that we have ADP and inorganic phosphate bound at the L site, now the thing's going to rotate as protons translocate across the membrane. So as it rotates, so most diagrams will not give you this kind of intermediate version. I just put it there so you can see which way things are rotating. I put them in the colors I did so that you could see what they're doing. So, but a lot of diagrams do a really terrible job on this part, and my apologies for that. So if you look, the red subunit, if you will, which was just a T subunit, turns into a what? An O subunit. And the O subunit is what releases the ATP. So now it does not have a great affinity for ATP anymore, so it lets it go. And that ATP that was freshly made, it's the same ATP that was down here, is now diffusing away. Cool. Also along the way, our L site, which had bound ADP and inorganic phosphate, as it rotates through this ADP and inorganic phosphate, so as this transitions from L to now T site, it turns it into ATP. There's your freshly made ATP again, another round. So And then we'll do the same process over again. Now we're going to bind some more ADP and inorganic phosphate to the L site. We'll do another turn, so on and so forth. So, but know definitely the O, L, and T and what they represent, what happens at each, so, and which directions things go as you rotate. So T goes to O goes to L goes to T. Question?
So does each subunit go through all three of those?
Each subunit will eventually go through all three of those. So notice right now, we started out with T down here. He just made some ATP. He turns into, right now, an O site. So in a minute, he's going to turn into the L site with another 120-degree rotation.
Why does it rotate?
So why does it rotate? Great question. It's the proton translocation. As the protons translocate, it's kind of like they're turning a rotor. So think about hydroelectric power is the best analogy I can give you. As water flows downhill, it actually turns a turbine. And those turbines generate electricity with generators, of all things. So this time, as the protons are translocating, flowing downhill with the gradient, so to speak, it's kind of like they're turning the rotor of the F naught, so which then spins the F1 ATPase as well. It's kind of a really interesting, cool process. You think this is actually going on in such a small little machine, and it really is. And you said earlier that this is really boring stuff, and I'm just like, really? Really? But it's okay. Questions right here.
Does each rotation just produce one ATP?
So each rotation is just going to produce one ATP. Well, each individual rotation of 120 degrees produces one ATP, but if you go through one full rotation of 360, how many ATPs will actually get created? 3. Cool, cool. So thanks for clarifying on that, by the way. Okay. Bless you. So we got one other little issue to talk about. So going back to glucose for a minute. Glucose, we oxidized it, so through glycolysis, forming 2 pyruvates. So, and assuming we're doing aerobic respiration here, so we got some issues. Where does glycolysis take place? In the cytosol. But where does the TCA cycle and electron transport take place? In the mitochondria. So we got a problem. So all of the NADH I make, so as part of the TCA cycle, is made in the mitochondria. And it's already there, ready to participate in the electron transport chain. But I made some NADH back here in the cytosol as well. And it's not in the mitochondria. And so if I want it to also participate in the electron transport chain, to pass off its electrons as well, then I have to shuttle it into the mitochondria.